In general, these wave functions follow the pattern I've just described. The quantum number goes up by 1 unit, but the energy eigenvalue is always an odd multiple. And there is a regular description for these polynomials. They're called the Hermite polynomials. That's probably not particularly important for us to remember. But do remember that they go like the 0th, 1st, 2nd, and so on, power of x. Perhaps something more important to remember is that they alternate whether they are even or odd. So notice that the 0th polynomial is an even function of x. The first polynomial is an odd function of x. The second polynomial is an even function of x again. So notice there's no x term in here. It's just x to the 0 plus x squared, and that's because this wave function is an even wave function. The third n equals 3 wave function has only the odd polynomials in it, so x and x cubed. And the fourth has only x to the 0, x squared, and x to the 4th. That's quite understandable, because if we think back to what our potential is, it's symmetric about the origin. And therefore we expect the probability density to be symmetric about the origin, and therefore we expect the wave function to have one of two possible cases. When I take the square root of an absolute value, well, I can get that by either having a plus or minus sign from the wave function. So psi of x is either plus psi of minus x, it's equal on either side, or it's minus psi of minus x. So these polynomials that I sketched at the very beginning here and that we had to do in our homework, that's polynomial 0, that's polynomial 1. That's polynomial 3. Excuse me, that's polynomial 2. And so on. These follow that pattern. Literally, if n is an even integer, then we get an even wave function psi. And if n is an odd integer, then we get an odd wave function psi.